So hello and welcome. This is going to be your first lecture on Lie algebras and Lie groups. So we have looked at discrete groups. We have looked at symmetries, which are discrete symmetries, and they lead to these discrete groups. And now we want to look at, things like continuous symmetry operations. Think about something that is rotation, right? Rotation can be about an axis. This can be viewed as this continuous symmetry operation, and so we will try and understand things like that, okay? And we will try and formalize that. So what we are going to be doing in this lecture and maybe the next one, because this is a bit long as well, is we will take you through an example that a lot of you already know. So a lot of you have looked at quantum mechanics, and a lot of you have looked at, angular momentum and the summation of angular momentum. Right. So as I was saying, so let's actually look at this now. So, as I was saying, we are going to be looking at continuous symmetry operations, rotations about an axis, that these can be viewed as, analytic functions of its parameters. When you're looking at rotations, this is just a continuous angle, of course, modulo 2 pi as I write here. So all of this we can understand as from the repeated action of one operator that generates this infinitesimal rotation about this action. We know, from classical mechanics and so on, that rotations about different axes do not commute in general. They would form a Lie algebra, and this is going to close under things that you are already familiar with, commutation relations. Okay, so what we will do here is that we will start off with the simplest non-trivial Lie algebra, which is SU2. This is something that you guys are, as I was saying before, you are already familiar with from quantum mechanics and addition of angular momentum. But it's good to have a look at this. Okay, so let's look at a two-dimensional Hilbert space, and this is spanned by the vectors 1 and 2. And we're going to take these three linear operators. Okay, we're going to call something T plus. We're going to call this is going to be this object, this bra and this ket. This is going to be T minus, which is the bra 2 and the ket 1. So for example, what T plus does is it sort of takes, if you look at, operating T plus on the state 1, then that gives you, that doesn't give you anything, but T plus on the state 2 gives you the state 1, right? So that is 1, 2, 2. So that just gives you 1. Similarly, the state T minus takes the state 1 to the state 2, and T3 is something else that you'll find. Okay, so this is T plus and T minus, and so if you look at T plus T minus, this is going to be the you're going to look at these two operators. So you want to first do T plus. This is T plus T minus, and this is T minus T plus. So as you can see very clearly, this is going to give you 1. So this goes away. This is going to give you 1. This goes away. So at the end of the day, what you're going to end up with is 2T3. Okay. You can also do the rest of the analysis, and you can find out what T3 with T plus minus is. You'll find out that this is plus minus T plus minus. Very good. Now we can define Hermitian operators. We're going to call them T1 and T2, and one will be defined as the sum, and the one will be defined as the as the difference. And then what we will see is, T1, T2, and T3. These three close amongst themselves by an algebra like this. This epsilon ABC is the familiar Levi-Civita symbol. If you're not familiar with this, it is just epsilon 1, 2, 3 is equal to epsilon 2, 3, 1 is equal to epsilon 3, 1, 2 is 1, and the odd permutations like 1, 3, 2, which is also 3, 1, 3, 2, 1, which is epsilon 2, 1, 3. This is equal to -1, and epsilon of any repeated index Iij is equal to 0. Okay, so this is what the epsilon symbol signifies in shorthand. Instead of, let me drop this. All right, so that's the algebra, and this algebra is actually very well known, and this is called, okay, so so this algebra also closes, as we see here, it closes under so this we have seen that this closes under the generators close, right? An algebra is called a Lie algebra if it also satisfies the Jacobi identity. So that essentially is T A, T B, T C, and its cyclic permutations have to add up to 0. In our case, you would be able to, it's trivial to show that this is the case. And so now what do we have? So this particular algebra, which is a very simple looking algebra, is a very, very important one. Okay, this algebra is called A1, B1, or C1 by maths people, or this is called SU2, SO3, or SP2. All of these things are the same at the algebra level. So we will get to this afterwards, and we will try to make links with that. Okay. Now, any polynomial function that is commutes with the Lie algebra. So any polynomial function of the elements of a Lie algebra that commutes with all the generators of the Lie algebra is called Casimir operator, as I say here. Now, in this case, again, this is something that you guys know, and this is in this case there's only one, and this is a quadratic one. So this is T1 squared plus T2 squared plus T3 squared, and you can check that this is equal to 0. So this is J squared, if you wish. Okay, so I call these things T, but you would be more familiar trying to call them J. But anyway, we will keep to our T's. So now, what do we have? We have this, our explicit. What we have written is an explicit construction of an explicit representation of this algebra in a two-dimensional Hilbert space. This is a first, if you wish, first representation is a 2D irreducible representation of S2, and it's going to be written by 2, and we're going to put a dash under it. What we will also see, what we have seen here is that these generators T plus minus If you square it, that gives you 0. This is not I mean, property of the algebra as such. This is a property of this particular two-dimensional representation that we are looking at. Okay, moving on. Now, so let's try to go a bit more into this. So let's note a few points. Again, a lot of this is going to be very clear to you from earlier, but this is sort of to reach out your memory about angular momentum and the addition of angular momentum. So in quantum mechanics, as you remember, a state is going to be labeled by what is called the complete set of commuting observables, or these are the eigenvalues of the maximal number of commuting operators. So in this case, this is going to be C2 and any one of the TAs. Okay, and what we will do, as you will remember, this is J squared and J3. So we just call this C2 and T3 here. So the algebra is going to be represented on the eigenstates of these particular operators. Okay. Now we see that C2 is something which is squared of T1 and T1 squared plus T2 squared plus T3 squared. It's positive definite. Hence the spectrum is going to, of any of these TAs is going to be bounded for any finite C2. Okay. Let's look at this. Let's try to see what we mean by this. So we are going to label these things by C and M. So C2 is going to be the eigenvalue of this this state, and M is going to be the T3 eigenvalue of the state. Since we have C2 and T3 as a Hermitian, C and M will have to be real as well. Now we have T plus. This raises the T3 eigenvalue by 1, does not change C2. So if we apply T plus on this, there is going to be some T plus, and we are going to move from the state Cm to the state Cm plus 1. Okay, we will determine D plus M later, but we can generate an infinite number of states with these T3 eigenvalues, M plus 1, M plus 2, and so on. But what we will see, what is going to be the case is that the spectrum of T3 has to be bounded, right? So the sequence has to stop at some point. Okay, so there is going to be a state. So the point essentially is that for a fixed C2, for a fixed C, there is only so much M that you can have, and so it has to stop somewhere, right? So this spectrum of T3 has to be then bounded, and the sequence has to stop. So there has to be a state, where T3 acting on this state is going to be equal to is going to give you its maximal value. So you cannot raise this more. Okay, so if you act T plus on this, then that has to give you a 0. This particular state, which we are going to represent as Cj, has to be the this has to have the maximal value of T3, and this is going to be called the highest weight of this particular representation. So let's remind ourselves of what C2 will be on this state. So if we act with C2 and then we do the algebra, this is again straightforward for you to check that what, so you can just do this and see that this is going to be j into j plus 1 c j. Okay, so c is going to be j into j plus 1. So just to so you what you do is you write this thing down, and so the thing that you have to keep in mind is that you have to use that t plus acting on cj is equal to 0, and then you would be able to go from step 1 to step 2. Okay, I urge you to try and work out the details. Again, this is something that should be something that you would have done earlier, but it's good to just get a hang of this thing again. Very good. So the maximal value of so what we're going to so the maximum value of T3 is determined by what the Casimir operator is. So what we do is, instead of labeling it as C and M, we just label it as J and M. Okay. Similarly, we can actually go down as well. So we can lower the states, and we can lower this by acting repeatedly with T minus now instead of T plus. And again, the process has to end somewhere. So there has to be a sort of lowest weight state where T minus acting on this will have to be equal to 0. Okay. And let's also remind you that T3 acting on it will give you this K. Now K is in the sequence where it can be J, it can be J minus 1, it can be J minus 2, and so on and so forth. Now remember that this particular state is also labeled by the same J. Okay, the C2 value is fixed, the C2 eigenvalue is fixed. So it has to, so you can now impose the fact that this has the same C2 eigenvalue. If you just look at the state and figure out what C2 on this is, then it comes out to be K into K minus 1. Okay. Now what we have is K into K minus 1 has to be J into J plus 1. So there are this is a quadratic equation, and there are only two ways to solve this. So either K has to be J plus 1 or K has to be minus J. Now we have already said that K is less than J, so K can't be J plus 1. So what we end up with is K is minus of J. So now what do we have? We have that any SU2 representation which is irreducible, this will contain J plus 1 states with the T3 eigenvalue ranging from minus J to plus J in integral steps. Okay, so that's good. Again, this is something that you guys have worked on before, but it's good to have it's good to revisit what you had learned before. Okay, so we have J. J is called the total angular momentum by physicists, as you know, while 2J is something called the Dinkel-Nabel of the representation by maths people. We will see a little bit more about Dinkel labels as we go forward. Okay, so now what we see is that the algebra of SU2 has an infinite number of irreducible representations, one for each integral value of 2J. So J equal to 0 is going to give you the trivial singlet representation. J equal to half is going to be something that we call this spinorial representation. J equal to 1 gives you the vector representation, and so on. So remember that there is something that we did not get done. That was figuring out what this factored in front of these guys would be. So T minus acting on Jm lowers the M eigenvalue and keeps the J fixed, but there is going to be something in front of this, right? So this is something we need to figure out. So so what do we do? So what we do is reasonably straightforward again. So we first recognize that d. So just by looking at this equation, we see that d plus of m minus 1 and d minus of m is minus dm. D plus of m and d minus of m plus 1, that has to be equal to 2m. Okay, and we also need to keep in mind that jm with jm primed is delta of mm primed. We can use this, and this is going to be left as an exercise for you guys to figure out that d m plus minus d plus minus m is given by a form which looks like this. Okay. Now, a point to note is that 2j has to be integral. So what you can do is you can start off with the highest weight state, and by repeated action of this lowering operator t minus, you have to reach the lowest state, right? So if there are L steps to this, then 2j has to be equal to L, or j has to be L by 2. So this is, j has to be half integral. Okay, very good. It is it's of use to represent these SU2s in terms of j plus 1, 2j plus 1 cross 2j plus 1 matrices. And these matrix elements are going to be given by the following. So if you have jm prime and jm, it's clear that this has to be m into delta mm prime. If you have a t plus which is sandwiched between them, then this is going to have a prefactor of something like this in front. And if you have a t minus, again from what we have done just now, we will see that this is this. So it's clear because this has to be delta mm minus 1. So what we can do now is that we can define the spin j representation of SU2 as the following. So this is what we have. So if you look at the k-eleth, k-eleth element, this is going to be given by this form. So now, so what is left is again, what you can do is often, as I write here, convenient to label rows and columns directly by their m values, which are just j plus 1 minus L or j plus 1 minus k. In this particular way of trying to do it, what you'll have is t a j. So again, let me not read this out, but this is what you have. And remember that j and m and m prime run from plus j to minus j in steps. Okay, in steps of 1. Now, for example, the j equal to half and j equal to half representation of this is going to just give you that t1 is going to be half of sigma 1, t2 is half of sigma 2, and t3 is half of sigma 3, where sigma i's are your Pauli matrices. This is going to be, this is again something very well known to you guys, and this is going to be called the spin half, or spinorial representation of SU2. This is what is the defining representation and also responsible for its name SU. So you can see that SU. So it's special unitary two-dimensional representations. So this is sort of like the defining representation for SU2. Okay, so that was that. So I would urge you to try to work out these things that I have showed you here, and maybe try to see if you can explicitly write down what your spin 1 representation would be. We will work on this more as we go ahead. But yeah, this was the first look at Lie algebras for you guys. We will work on, so, and I thought I would start off with something that you are already familiar with, and then we are going to build on this. All right, so that's all for me at the moment. So this is where we will stop for now, and then let's again resume with this in a little while. All right then, yep, that's all for now.